Today we are going to look at section 2.4 from your book, where we're going to talk briefly about the fundamental theorem of algebra. So as you see on your paper, the fundamental theorem of algebra states that a polynomial function of degree n, where n is greater than 0, so we're not including constant functions here, has at least one zero that's either real or imaginary in a complex number system. So the corollary is what we really focus on, though, with the fundamental theorem of algebra. So that says a polynomial function of degree n has exactly n zeros in the complex number system. So that's telling us that the number of zeros or the number of solutions should match with the degree of the function. We have to keep in mind that if a 0 has a multiplicity greater than 1, then it's taking up more than one spot in our list of possible zeros. But that should match the degree of the function. You also have another theorem here that's called the conjugate root theorem. This theorem says when a polynomial equation in one variable with real coefficients has a root in the form a plus bi, so it's important that we focus on that there as our format that we're looking at, so a plus bi, where b does not equal 0. So if b equals 0, then that number would not have an imaginary component. So most of the numbers that we deal with each day are real numbers. All real numbers are numbers that have a b of 0. So you don't see the imaginary part. But we're focusing on those that do have an imaginary component. Then they have a complex conjugate. So basically they have a partner of the form a minus bi. That is also a root of the polynomial. So imaginary numbers is how you're going to see them, because you're going to think imaginary when you see the I. Those travel in pairs. A plus bi has a partner or a pair in a minus bi. So if we look at the first example here, it's asking us to write a polynomial function of least degree with real coefficients in standard form. So that seems like a whole lot. So we're going to pick this apart. So standard form, remember, means that your degrees get smaller as you move across your terms. Where it says real coefficients, that means that your coefficients on your terms are not going to involve an I. If they do, we've done something incorrectly. And then this least degree is going to enable us to assume that the list of zeros that they give us is the list of all of the zeros, not that there are others that are unlisted. So if we take a look at this here, we basically are going to be working backward through the process of solving. So I have been told here that we have zeros at -1, so that means x equals -1 is one of my solutions. That's bad. Let's try that again. So x equals -1 is one of your solutions. Also, x equals 2 is one of your solutions. And then they also tell us that 2 minus I is a solution. And if 2 minus I is a solution, then that means that its complex conjugate, which is 2 plus I, also has to be a solution. So in this case, we have 4 solutions. So if you think with me about the process of solving, each of these solutions would have come from a place where they were originally set equal to 0 and then solved. So we're going to work towards getting those now. So if I got the answer x equals -1, then that means that would have come from the factor x plus 1 equals 0. For x equals 2, that would have come from the linear factor x minus 2 equals 0. Now, if you think with me about x equals 2 minus I, so if this is going to be set equal to 0, then I'm going to need to subtract the 2 and add the I. So for that one, I would have x minus 2 plus I. And then for our last one here, if we have x equals 2 plus I, then that would have come from x minus 2 minus I. So we're going to think backwards again, even more here. If I have all three of these that are now set equal to 0, then these in factored form would have been the things that we had in each parenthesis. So what we are able to say is that in factored form, our polynomial would be, so I'm going to call it f of x, and I am going to use this space down here for this next example, and I will write that on a different screen. So for our polynomial, if I call it f of x, then we will have x plus 1 times x minus 2 times x minus 2 plus I, and then times x minus 2 minus I. So this is factored form. To get to standard form, that means we have to do some multiplying here. So this is going to take us some work. So as I start to multiply this, with these first two terms, never work with more than two terms at one time. So for the first two terms, I'm going to need to FOIL. So when I'm FOILing there, I will have x squared minus x minus 2 and then when I go over here to look at what I have in this second parenthesis, this is where it's going to be a little more work. So I need to make sure that everything in parenthesis 1 gets distributed to everything in parenthesis 2. So I'm going to start with this x, and I'm going to do this in a different color just to help you follow the work a little bit better. So I'm going to distribute the x through. So x times x is x squared. X times negative 2 is minus 2x. X times negative I is minus ix. Then I start through my next round. So this time I'm distributing negative 2. So negative 2 times x is, again, negative 2x. Then I have negative 2 times negative 2, which is positive 4. That does not have any like terms from the row before, so I'm going to write that here. And then negative 2 times negative I would give me positive 2i. Again, I don't have any like terms, so I'm going to just write that over here in its own column. And then the last thing I have to distribute through is this I. So I times x is positive ix. Then I times negative 2 is minus 2I. And then I times negative I would give me negative I squared. Okay, so if I look at what I have now here, hopefully you notice that we have some like terms, they're aligned, but specifically that some of these pairings are going to cancel. So negative ix plus ix, that's going to cancel. 2I minus 2I is also going to cancel. And then I have this I squared. So I squared, you learned in Algebra 2 Honors or in regular Algebra 2, either of those, that I squared is equal to negative 1. So that means that this negative I squared that we see here is actually going to become minus negative 1. So that's going to align over here as plus 1. So now I can sort of start to put this together a little bit more. So I have f of x equals, so I still have that first polynomial. So x squared minus x minus 2. But then in this green polynomial, now I have x squared minus 4x plus 5. So we have one more round of multiplying here. So we need to make sure that we get everything again in parenthesis 1 multiplied to everything in parenthesis 2. So as we start to work this through, I'm going to take the x squared through first. So that gives me x to the 4th minus 4x cubed and then plus 5x squared So now I'm going to go back through with the negative x. So negative x times x squared is negative x cubed and then I have negative x times negative 4x would become positive 4x squared. And then negative x times 5 would be minus 5x. And then finally, I'm going to distribute through the negative 2. So negative 2 times x squared is minus 2x squared. Negative 2 times negative 4x would be plus 8x. And then negative 2 times 5 would give you minus 10. So now I just have to combine my like terms. Again, they're already organized vertically to see what I have. So I have that the function f of x is equal to, so I have x to the 4th minus 5x cubed plus 7x squared plus 3x minus 10. So that is your first function. Moving on to the second example here. Something that's important to know is that just as your imaginaries travel in pairs, so do roots like this one, 2 minus radical 3. So that's an irrational root. When you have a radical that contains a prime number, it's irrational. So it also is going to have a conjugate that travels with it, which would be 2 plus radical 3. So that means that we know that we have 4 solutions here to this polynomial. So we have x equals 2 minus radical 3. We have then its conjugate, which would be x equals 2 plus radical 3. We also have x equals 4 plus 5i. And then its conjugate would be x equals 4 minus 5i. So we again need to think backwards from these to figure out what are the parentheses that they came out of, knowing that those parentheses would have originally been something set equal to 0. So I'm going to go ahead and write these into their parentheses down here. I'm going to call this polynomial g of x. So 2 minus radical 3 would have come from x minus 2 plus radical 3. Then we would have x minus 2 minus radical 3. And then you would have x minus 4 minus 5i. And then finally you would have x minus 4 plus 5i. So this is our factored form, but we again have the same goal of trying to get this into standard form. So we are going to need to do some multiplying here. I know that this is going to be ugly in the beginning, but it should pretty quickly clear itself up if you multiply the pairs together that match. So the conjugates need to be distributed to one another instead of just multiplying in any order to make sure that this doesn't get too out of hand on you. So I'm going to start with the first 2 parentheses that you see here. So I need to distribute through the x, and then the negative 2, and then the radical 3. So x times x gives me x squared. X times negative 2 would give me minus 2x. And then x times negative radical 3 would give me minus x radical 3. So then I need to distribute through that negative 2. So negative 2 times x is minus 2x. Negative 2 times negative 2 is plus 4. I should have aligned these for you. Let me move this. So I'll align your terms for you, sorry. So minus 2x. And then we said we had negative 2 times negative 2, which would be plus 4. And then negative 2 times negative radical 3 would give you plus 2 radical 3. And then finally, I need to take the radical 3 through. So radical 3 times x gives me x radical 3. Radical 3 times negative 2 gives me minus 2 radical 3. And then radical 3 times negative radical 3 would give me negative square root of 9, which is negative 3. So I have my like terms all aligned here. So hopefully you notice here again that much like the last one, we see some things cancel out. Negative x radical 3 and positive x radical 3, those are going to cancel out. And then 2 radical 3 and negative 2 radical 3 are also going to cancel out. Meaning that at this point, you have x squared minus 4x and then plus 1. But we do still have these other two parentheses up here. So we have x minus, I guess that your first one says plus, no, it was minus, sorry. So x minus 4 minus 5i. And then you also have x minus 4 plus 5i. Okay, so now we need to go through and we need to multiply the two right side parentheses together. So when I multiply those, the process is going to be the same. So x all the way through, negative 4 all the way through, negative 5i all the way through. So x times x gives me x squared. X times negative 4 gives me minus 4x. And then x times 5i gives me positive 5ix or xi. It doesn't matter what order you write those in. Next, I have my negative 4. So negative 4 times x gives me another negative 4x. Negative 4 times negative 4 would give me positive 16. So I don't have anything that's a like term with that from the step above. And then negative 4 times 5i would give me minus 20i. And then finally this negative 5i has to go through. So negative 5i times x would give me negative 5ix. Negative 5i times negative 4 would give me positive 20i. And then negative 5i times positive 5i would give me a positive 25i squared. So hopefully you notice here again that you have pieces that are going to cancel out. So 5ix and negative 5ix cancel out. negative 20i and positive 20i cancel out. So if I combine what I have here, then I have x squared minus 8x. And then over here where I have this plus 25i squared, we said I squared is like negative 1. So that means this is actually going to move over into this column as a negative 25. So 16 minus 25 would give us negative 9. So I need to multiply this with the polynomial that I already had, which was x squared minus 4x plus 1. So this multiplying should be the easiest of the 3 rounds that we've done here because you don't have any radicals or any i's involved. Same goal, everything from parenthesis 1 needs to get multiplied to everything in parenthesis 2. So x squared times x squared would give you x to the 4th. So we have x to the 4th. X squared times negative 8 would give us minus 8x cubed. X squared times negative 9 would give us minus 9x squared. Now I need to take the negative 4x through. Negative 4x times x squared will give us negative 4x cubed. Negative 4x times negative 8x will give us a positive 32x squared. And then negative 4x times negative 9 will give us a positive 36x. And then finally, the 1 needs to go all the way through. So 1 times x squared is x squared. 1 times negative 8x is minus 8x. And 1 times negative 9 is minus 9. So if I combine my columns now, I should have my final answer. So x to the 4th minus 12x cubed see, 32 minus 9 would give you 23, so 24 x squared. $36 minus 8 would give you, again, a positive 24x. And then minus 9. All right, so look at your notes and you should see your assignment listed on there. Work through that before you start on the next section.